Good morning. This is lecture 4 for the mechanical vibrations course. So the agenda for today is modeling several examples, getting the equation of motion, and from that arriving at the natural frequency of vibration. And this is using Newton's law because next time, in the next lecture, we're going to be doing the same type of thing, arriving at the equation of motion based on the energy method. But today is Newton's second law. And there will be several problems that we do where uh, the effective stiffness of uh, springs have to be calculated. Now, the other thing I want to point out too is that this course is all about linear vibration. In fact, most of your undergraduate career deals with linear problems. Now, one of the two things that are extremely important when dealing with linearization are these approximations to sine x and cosine of x. For example, the sine x, as the Taylor series is given right there, and notice that when x is small, the power of x is a lot smaller than x itself, and therefore, very frequently, these things are all dropped, and therefore, sine of x is approximated with the x itself, and therefore a linear problem has been arrived at. Now, cosine of x has this Taylor series expansion that you see here, okay? And uh, if I keep the first two, because these are all a lot smaller than x itself, and if I drop all of these, I get that expression, but this is still a nonlinear expression. So for x small, if I ignore this thing with respect to 1, we're going to get cosine of x is approximately equal to 1 when x is small. Now, if you look at the tangent, I've not written it down here, but if you look at the tangent, tangent is the ratio of sine x over cosine of x. And if I say that x is small, sine of x is close to x, cosine of x is close to 1, so tangent of x is close to x over 1, which is x. Therefore, tangent of x enjoy the same kind of linear approximation, which is approximately x. All right, so the first problem that we're going to do is rolling of a disc on a surface, as you can see it here, and there's a spring that is attached from the wall to the center of the disc. If I assume that the disc rolls without a slip, the angular position of the disc and the displacement of the disc, these are related by a simple expression r theta. So think about it as x equal to r theta. You have to be a little bit careful about the sign here, sign as in algebraic sign, but roughly x is r theta. We'll get there in a minute. Now, if the disk not only moves, but it also slips, then this becomes a 2 degree of freedom system, which is the last 4 weeks of the course, okay? So we're not assuming that, we're assuming that this is rolling without a slip. The other thing is that if the disk is attached to the top location of the disk, then the problem slightly changes, okay? And we will do that later on. The natural frequency changes, the equation of motion changes, but the steps are fairly similar. We'll do that later. Now, the key to getting the correct expressions for this problem and many other problems is what we taught you in your second year dynamics class, rigid body dynamics. Basically, it says the velocity of any point, such as the center of the disk, is equal to velocity of some other reference point, such as the contact point that you see down here, the contact point, okay? Uh, Plus angular velocity of the object, two-dimensional object in this case, the disk, crossed with the position vector from the center to the contact point. Let me remind you that this was taught, you were taught this thing as velocity of A is equal to velocity of B plus omega crossed with R of A relative to B, okay? But here the A and B are the center and the contact point. Now, a couple of things you realize is that the contact point, which is this location where the two come in contact, has no velocity because that's the ground. Therefore, the velocity of the contact point is the zero vector. Now, The center of the disk, on the other hand, is moving only in the x direction, so its velocity vector is x dot, okay, x being the displacement of the center, and I is the unit normal along the x direction, and crossed with the position of the center with respect to the contact point is just a j vector, the unit vector in the in the y direction multiplied by the radius of the disk. Now, if you write this thing in detail and clean it up, you're going to get x dot equal to minus r theta dot I. If you write this thing, x dot dot I is repeated, 0, we don't worry about it, and k crossed with j is minus I, and therefore we get this. If we drop the I, we look at only the scalar values, we get x dot equal to minus r theta dot. Now, that minus should not surprise you, because as the disk moves to the right, x becomes larger and larger, and if this is rolling without a slip, the direction of actually rotation of this disk or wheel is opposite to what I have assumed here. I have drawn it like that in the counterclockwise direction, but actually if x moves to the right, the actual rotation is in the clockwise direction. And that minus sign in the expression that you see here, in this expression, is because of the way I have assumed that theta varies. Okay? Now, notice that this last expression, x dot equal to dot dot dot, if you differentiate it again, you get x double dot equal to minus r. R doesn't change the radius of the disk, theta double dot. And if you integrate it, you get the position of x, of the center, which means x is negative r theta. Okay. Now, so the Newton's second law in terms of moment is the sum of all the moment about the mass center. For example, O is equal to polar moment of inertia with respect to O times the angular acceleration. Angular acceleration, uh, obviously, you talk about theta double dot, okay? Angular acceleration is theta double dot. So if you write things down, the right-hand side is JO, polar moment of inertia. Angular acceleration is theta double dot in the k direction, okay? And the only force that has a moment here is actually that friction force, okay? The spring force that you see that in this free body diagram, the spring force Fs does not have any moment about O. The weight of the disk, mg, does not have any moment about O because it goes through it, and the normal reaction also goes through O. So these three forces do not contribute to the moment. The only one that contributes is actually friction force. Okay? And in fact, because of the way I have drawn my direction of theta, the moment, the moment, uh, the moment of this friction force about the center O is negative, because think about it like that. X and Y are, as you should see here, Z is coming towards you. This force that you see up there, this friction force, has a negative moment, because if you curl your fingers so that your thumb points in the Z direction, that force is actually creates a moment opposite to the direction of positive direction of Z. Okay. Now, so basically, what you see here, is exactly that expression, except that for theta dot, I have replaced it from the previous page, x dot over r. Remember, we got x double dot. In the previous page, we got x double dot equal to negative r theta dot. So I've replaced theta double dot with x double dot. Now, this is the same thing, except that I've divided through by r, which is fine. So just keep in mind that this is the friction force which causes rolling. Now, if you look at the Newton's second law itself, not in terms of moment, in terms of linear acceleration, sum of all the forces in the x direction is equal to mass times acceleration in the x direction. Okay? So basically what you see there is true. And the only the forces that are acting in the x direction, they're both negative, and the point is they're minus Fs and minus F friction. And of course, mx double dot is written there. So the only force that you have, the vector equation, is in the I direction, obviously. Now, the force of the spring is the stretching of the spring, which is x. We're assuming that it is moving from the equilibrium position. The stretching of the spring is x times the stiffness of it, kx, is going to be the spring force and the minus sign because it points to the left. And friction factor, obviously, friction force is also the way I've drawn it, it points to the left. Okay. And we have the friction force from a few lines above it given exactly, oops, let me see, I'm going to go back for a second. Friction force, negative friction force is right there. So if you substitute it here and clean this up, take everything to the left-hand side and factor x double dot, you're going to get that this is the mother of all equation for this particular problem. Now, if you look at this, what it tells you is that you have a vibration problem. And the stiffness of the problem, there's only one stiffness involved here, and that is K. But the mass has to be replaced with this expression. If yeah, the mass has to be replaced with this expression. Therefore, I'm going to write it again here. And the JO for a disk is 1/2 polar moment of inertia, but the center is 1/2 mr squared. And if you take this thing and stick it in there and clean it up, you get 3/2 mx double dot plus kx. Therefore, the natural frequency of vibration of this problem, if you move the disk and let it go, let it oscillate back and forth, rolling without any slipping, the frequency of that oscillation in radians per second is going to be given to in this form. And in the event that you plug in the value of JO, you get 2/3 of K over M. Okay? Now, I'm making a comment here, and that is because the friction force, when I was trying to set this up for you, I drew it to the left. If you don't know what the direction of the friction force is, there is actually some kind of a direction, and you assume that this way, and you go through all the steps in a systematic way, you will end up with exactly the same equation. Do this thing, except that this time the spring is attached to the top point. And if you wonder how can you do this, imagine that there is a cable wrapped around that, like a yo-yo, a cable wrapped around that disc, and at the end of the rope there is a spring attached to the wall. Again, rolling without any slipping. First of all, as far as the kinematics is concerned, this is exactly what I wrote before. No distinction here, okay? And if you follow the same approach, you get exactly the same kinematic equation right here. These three are exactly what we had before, okay? Now, if you look at the velocity of the top, acceleration of the top, and position of the top, it's going to be the same thing except that the distance from the top to the contact point is 2r. That's why if you wrote these systematically based on the equation that you see there, the only difference is that instead of r, you have 2r, okay? This is in terms of theta. If you write it in terms of theta, you can also find here theta is going to be x over 2r, right? X over 2r. You take these things and you plug it in there, you're going to get in terms of x. The velocity on the top is basically twice the velocity at the center, etc. Because x dot is the velocity of the center point. Velocity of the top is twice that, okay? Because you can see that if you visualize this thing in an intuitive way, this top goes faster than the center point. Actually, it goes double the velocity. Okay, so let's look at the equation free body diagram here. It's exactly the same thing, except that the spring force is way on the top. Spring force is way on the top. So everything is the same, except that we have to write moments in terms of the forces that you see there. Once again, N and mg do not contribute, the normal force and mg do not contribute to the moment about O, but both of these will. Last time, Fs did not give you any moment because it went through the point O. Here, they do. And if you look at if you draw your friction force like this, based on the discussion that we had in a minute, a few minutes ago, if you draw it like that, the only difference is that when you take a moment, you also have to take a moment of the force Fs about the point O, and that's just Fs times R in the K direction. And in fact, look at, because of what I've done here, the direction of theta rotation, my positive direction of theta rotation, this is going to give you a positive moment, okay? Just curl your finger, look at the direction of the thumb. All right, so we have an additional term that's popping up here. Before we didn't have this. In the middle, we didn't have it. Now we do, okay? And just divide by R, same as before. And the only thing is that this Fs, the force of the spring, is actually the stretching of the string at the top point, and that is, in fact, X at the top. Before it was Kx, X at the center, because the spring was stretching right here at in this direction. Now it's on the top, so it's the displacement of the top point that is important. And we know what the displacement of the top point is. It's twice the displacement of the center point. So that's what is done here. And plug in x top equal to 2x, x being the displacement of the center. And we also write the equation sum of all the forces equal to mass times acceleration. This is the actual Newton's second law, and both Fs and friction are participating just like before. This is the same thing that we had before, and you plug in the stuff that you know. For Fs, we just got x top times k, stretching of the spring, times stiffness of the spring, and friction, we got it from here, right there. Just plug these things in and clear it up, okay? So this arrow means that I'm taking the expression for friction from here and just sticking it in there and cleaning it up. The only difference that we have, that 4 in front of K, it was before 2K, okay? When the spring was at the center O, attached to the center O, that 4 became a 2. And natural frequency, if I assume that JO is 1/2 mr squared for a disk and clear it up, I get AK over 3m. For the previous case, natural frequency was square root of 4K over 3m. Okay, so let's move on. The next problem that I want to do for you using Newton's second law is this manometer, which is perhaps, well, filled with the liquid, and perhaps you push the liquid down on one side by blowing at it or pressurizing it. So the other side, the liquid will go up, and if you remove the pressure, this starts oscillating back and forth. Now notice that here I have drawn this to be length L. From here, in other words, the length of the fluid, like so, to be L. This is going to play a role here later on. The restoring force is the gravity force. Now remember, every problem that we have done so far was a mass and a spring. Okay? Now, there was a spring literally present, and in fact, the spring was what caused the mass to go back. The mass moves, for example, to the right, spring pointing in the opposite direction. So it's the fight between the inertial force, which is mass times acceleration, and the restoring force, which is kx. That's what we did before. Here, we don't have a spring. The restoring force is not the spring force, it is the gravity. And you will see that it's going to be the weight of the displaced liquid. So here's the situation. We're going to get that, but first of all, we're going to assume for this derivation to be easily understandable, we are going to assume that these tubes are very close to each other, so we neglect basically that portion, okay? And so if you look at the drawing here, this side goes down by x, this side goes up by x. So actually, the thing that causes the fluid to go back and forth is the displaced liquid, which is a fluid of height 2x. 2x, not x. It's this thing that when it goes up, it's going to try to push it down based on its force of gravity, its weight. Okay? So if you look at the column of height 2x here of liquid, that's this piece that you see there, this piece, height 2x. What is acting on it? First of all, it's the weight. The weight is the height times the area is going to give you the volume of it times the weight density. This weight density is just density divided by g. That's what it is, okay? Or a specific weight of the liquid. So the force acting down is actually this. And what is the acceleration? Acceleration is x dot, but what is the m? The m is not the m of this portion. M is the entire liquid, because what this oscillation is doing is moving the entire liquid, and that's this piece. So if you look at it, L times A is going to give you the volume of the entire liquid, and multiplied by gamma divided by G, this is the mass of the entire liquid. In other words, from here all the way to the top. From here all the way to the top. So this is the equation of motion. Force equal to mass times acceleration. They're opposite direction. So one is negative, force is negative, the other one is positive. And clean it up, you get L over G x double dot plus 2x equal to 0. This is the equation of motion, the mother of all equations. So L over G plays the role of mass. It's not mass, but it plays the roles of mass. And 2 plays the role of stiffness of something. It's not really stiffness, because the gravity is causing the restoring force. There is no spring there, okay? And if you take the square root of k over m, this is k is 2, m is L over G, you're going to get this. And this is the natural frequency of vibration of this column of water. Okay. So gravity in this particular problem, the one that I just showed, does play a role, because G appears in it. G appears in that expression. So it plays a role. Now, here is my next problem. So you have a bar hanging from the ceiling, and this bar has a length L, and I've written stiffness equal to E over A, K equal to E over A. At the end of it, there is a mass. As soon as you see E over A here, you should realize from your deformable bodies or from a stress analysis, you're dealing with axial stiffness. Axial stiffness. So when you're talking about vibration of this, is in the axial direction. That's why the X that's drawn there, you can see its deflection along the axis. Okay. Now we're going to ignore the mass of that bar. Next time in the next lecture, we're going to see what needs to be done if the mass of that bar needs to be taken into account, because it does play a role, but it may not be significant. Now, so the only mass that's in sight is that mass m at the end. Now, first of all, here is an explanation of why the axial stiffness of that bar is EA over there. Let me remind you, from deformable bodies or from I don't know, stress analysis. The stiffness of that structure, this is like a fancy spring. This bar hanging is like a fancy spring. And the stiffness of a spring is the force applied to it over the amount of stretching. We know this. That's what it is. Force over stretching. Now, force in that bar is the stress in the bar times area, because that's how axial force, axial stress is defined. Sigma is F over A, or F is sigma times A. We leave the delta L, and because the problem is linear, the stress in the bar is Young's modulus times strain in the bar, right there. So sigma is equal to E Young's modulus times strain. And the strain, by definition, is changing length over the original length. Notice that the changing length disappear, and you get EA over L. So this is the stiffness of my axially loaded member. Now, if that is the case, I have a mass, I have a fancy spring with that stiffness. You can find its natural frequency of vibration up and down as stiffness over m. Put the k, whatever you've got here, and you have square root of EA over ml. Now, E for Young's modulus for different materials are given in this table. And I don't need the density of it here because I'm not taking bar into consideration. I'm looking at the lump mass at the end. So this is a table which gives you Young's modulus basically of different materials, okay? The last column is the shear modulus, which incidentally down here is defined in this red line, red expression. So if you know the Young's modulus and the Poisson ratio, you can actually generate this column. Now, we don't need G in this particular problem, but when we have torsional problem, G is more appropriate. It's going to pop up in the expression for mother of all equations. Okay, let's move on. So here's the same situation, except that the vibration is taking place in the transverse direction. From strength stress analysis or deformable bodies, the bending stiffness of this beam is 3EI over L cubed. Okay, and so basically, again, square root of stiffness, which is this ugly term, 3EI over L cubed, divided by m. So there's the stiffness. Force, uh, force over stiffness is force over displacement. Okay, here's the displacement. Your displacement from deformable bodies or stress analysis is given for a cantilever beam is given FLQ over 3EI. Clean this up, you get 3EI over LQ. This is the explanation of why the bending stiffness is 3EI over Q, 3EI over LQ. Because if you know the tip deflection, you can find this ratio, and that is going to give you exactly what the stiffness means, actually. And you take this thing, plug it in K over M, you're going to get this stuff. Notice that the I comes into to play because this is a bending problem. Let's do a problem here. And the problem is an aircraft. This looks like an ugly aircraft, but let's assume that the fuel is stored at these end pods. Okay, you're told that you have if the fuel is maximum, then it's 1,000 kilogram, the weight, the mass of this pod, and if it's empty, it's 10 kilogram. And what you want to do is to find the natural frequency of vibration of the wing up and down. Okay, it doesn't matter, you take only one side. So basically you have a cantilever beam which is vibrating up and down, and these two doing the same thing. So we just look at this. And the properties of I of this beam is given to you. Somehow somebody worked out the I about the axis, the proper axis, bending axis. And it says 6.9 10 to the 9, that's the Young's modulus for aluminum. And the length of it is 2 meters. The length of the beam is 2 meters. Actually, this looks like more like a Cessna than an aircraft like that. This is 2 meters, very small. So it's an experimental aircraft or Cessna. Now, we don't need the bending moment shear force diagram, but it's a good idea to, I mean, these things should never escape you. You should know these, okay? So if you have a cantilever beam point loaded, the shear force is constant because you make a cut anywhere, the force that balances F is F, okay? And moment is maximum at the wall because F times the distance as you cut and you look at the force and then multiplied by the distance, it's going to be linear. The maximum stress, the maximum bending moment is at the fuselage, okay, at the wall, and that's because that's where the moment is maximum. Now, from again stress analysis or deformable bodies, the tip deflection is these are given in books, in your the back cover of your book probably, or the appropriate page when you do bending, and this should be hacked in your mind. This is a very important expression, FLQ over 3EI, okay? So if you have the tip deflection, you take the force and divide it by the tip deflection, you're going to get your stiffness, bending stiffness, which is right there, okay? Now, if you look at so basically we have a mass spring system. Mass spring system, the mass is that 1,000 kilogram if it's full, if the tank is full, or 10 kilogram if the tank is empty. So it's just going to be this K divided by the mass of the fuel, whether it's full or whether it's empty. So if you plug in the K from this expression and clean it up, you're going to get this, and plug in the numbers. Here is the full pod, the mass of the full pod. It's going to be 11.6 rad per second, which is 1 hertz cycles per second. Now, if you repeat this thing for when the tank is empty, the mass is only 10 kilogram. So empty tank, only 10 kilogram, right there, 10 kilogram, you can see that. Everything else is the same, and you get 18.5. So when you look at it, full tank, 1.8 hertz, empty tank, 18.5 hertz. So it's a significant change from a tenfold change. And these significant changes can actually affect the performance characteristics of the aircraft. Okay, so I mean, pilots, you know, fly accordingly. That's why training is important, obviously. So this dramatic change can actually make big changes in performance. What we want to do now is talk about torsional spring. Torsional springs are very common also. For example, in your door stopper, in the door, you have a torsional spring. If you have a mechanical watch, you wind it, it's a torsional spring, etc. So the relationship between the moment and angle is given. In the translational case, force and displacement, you take a spring, axial spring, and stretch it. The force that needed is K times X. Here, this is a torsional spring, so you have to apply a moment to kind of wind it if you want. And this is okay, torsional stiffness. I put a T here to remind you that this is the torsional stiffness times the angle that it torques. Okay. So, I mean, if you look at a problem like that, you think about it, a bar, a bar here, or something like that, cylinder made of steel or aluminum, whatever it is, and then there is a disc at the end. This is a very common configuration. For example, propellers, uh, ship propellers, or imagine even the rear axle, front axle of wheel looks like that. There is a shaft, okay, and then there is a disc, maybe flywheel, maybe the tire, etc., attached to it. So this obviously goes through torsional vibration. Of course, if you take this thing, shift it to the left, and let it go back and forth, it can have bending vibration, it can have axial vibration, but we're only, at least right now, we're only considering torsional vibration. So these properties are given. Be careful because the terminology in different books are different. Even in this course, sometimes you may see inconsistencies. For example, instead of JP, I might say IP in some examples. So it's both. You should realize that once you once you learn to this, then whenever something else arises which uses that, the variables may be labeled differently, but essentially it's the same problem. Okay. So this is the torsional stiffness of the rod. This being the rod, okay, which is repeated here. And so if you look at it, the thing that is the restoring force is due to the torsion of this bar, and it is K is given here, times the angle of twist of the wheel or this disc, okay? K is right there, and G is the material that the rod is made of, and JP is that same, is right here. JP for torsional purposes is uh, pi d to the 4 over 32, okay? Yeah, okay? It's right there. By the way, you might say, wait a minute, didn't you tell me it was 1/2 mr squared? Yes, 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 but m has an r in it. So this does not contradict 1/2 mr squared for example. But remember, this is d to the 4. So just be careful. Things like this you have done on numerous occasions in your machine dynamics class and your dynamics class when you did rigid body dynamics, okay? So the polar moment of inertia of the bar is, for this bar, is there. If you insist on using the formula 1/2 mr squared, you're talking about m of the bar, r is this radius, which is d over 2, etc. Just be careful. And of course, this is the inertia, and you clean it up, you get this. So if you're dealing with torsional vibration, J is what's going to pop up, okay? Which is J of the wheel. If this was a wheel or a disc, a solid disc, uniform disc, the J of this wheel will be 1/2 mr squared, okay? 1/2 mr squared. Or you can even use this, except that the D is the D of the disc, the D of the disc, not the D of the bar. So you got to be careful. And there we are. So if you plug in the value of K, which is given right up there or right there, and clean it up, you're going to get that expression. Okay, so here's an example. We have an automobile tire, which is attached to a rod, and you're given the diameter of the rod, which is 0.5 centimeter, half a centimeter, and it's 2 meters long. And you're told that this wheel, when you twist it, there's a mistake here. This should be 10. This should be 10. Makes 10 oscillation, not T0 oscillation. 10 oscillation. 10. Okay, so it makes 10 oscillation in 3.2 seconds. You're told that this is the property or shear modulus of this bar, ADGPA, which incidentally is what is for yeah, this Young's modulus for steel is 200 GPa or 206 GPa. Shear modulus, remember, you have to divide it by 2 times 1 plus Poisson ratio. It comes out to be this. You're asked to find the polar moment inertia of the wheel. You're asked to find J. You don't know what J is you're trying to find. First of all, the natural frequency of the structure, vibration of the structure is given here. And it is 10. 10 oscillations in 10 oscillations in 32 seconds, okay? So in 10 oscillation means 10 times 2 pi. 10 times 2 pi is going to give you radians, divided by 30.2 is going to give you 2.081 radians per second, okay? Good. This 10 and that time will tell you what the natural frequency is, okay? 10 oscillation in that many second is 2 pi times 10 radians in that many second, radians per second. That's the circular frequency, circular natural frequency. Now, we can also calculate JP because we know the diameter of the bar. Just plug it in, work it out. And if you have the G given to us, shear modulus, and JP we just calculated, and the length of the bar is 2, you can find the torsional stiffness of the bar right there. And the formula, we just discussed it a minute ago, is GJP over LJ, or actually K over J, but we know what K is. K is this ugly term, GJP over L. We just plug it in. And here we know the frequency is 2.081, circular frequency is 2.81. This guy, we just worked it out up there. Actually, we didn't work it out. I have to do that. I have to take the 80 and multiply it by JP. So, oh, sorry, right here. It's this. This GJP over L is right there, 2.455. And then you solve it, you're going to get your J. That was the desired entity. Okay, let me remind you about the helical spring. Now, if you say that, what the heck is that? Helical spring? Well, all springs are helical. Mechanical springs are helical. I mean, although we draw it as a jagged, a jagged symbol like that, I mean, when it comes to reality, it's helical. All springs are like this, whether it's the spring in your ballpoint pen or whether the spring that is in your shock absorber of the car. Now, uh, to find the stiffness of the spring, you did a machine design. It's got some expression like that. The material is important, appearing at G. The diameter of the, let's say, the rod, helical rod is important. It's over there. And then the R, which is the radius of the winding, and the number of windings. The more windings you have, the less stiff it is going to be. But anyway, it's right there. This was done in machine design course in your third year. Now, this table is coming from your Inman's book, but I'd rather show you an expanded version of this. In a few minutes, we're going to do a problem which involves this last one. Just be patient, and we're going to get to these in a minute, okay? So I'm going to do an example which involves this, okay? So let's see now. Axial stiffness of a tapered bar of length L, Young's modulus E, and end diameter D1 and D2. So I'm going to show you this. That's what it's talking about. Tapered bar, diameter D1, D2, length L, axial vibration. Okay. So the stiffness of this thing in the axial direction is given there. That's the first row of that table. Then the next one was the uniform 2. Okay, diameter, inner and outer diameter D1 and D2. Torsional vibration. Okay, that's the second row of that table. And that doesn't surprise you because we already seen G D to the 4 over 32L. Now, when you look at the fixed beam, that's the third row, or the last row actually, of that table, loaded the middle. The bending moment shear force diagram are drawn here, but that's really not the issue here. If you go to your strength of material stress analysis book, you see that the deflection in the middle is given, and if you take the force and divide it by deflection, you're going to get the stiffness equivalent uh, stiffness of the equivalent spring. Because after all, this is a spring. You apply force, it deforms. You remove the force, it goes back. And out of that basically you have a fancy spring, okay? And if you have a simply supported at the two ends and force is somewhere distance a away, this is going to be the stiffness of this. In other words, you apply a force, it's going to deflect by some amount, and if you take the force divided by that some amount, you're going to get the stiffness, which is going to be very frequently this F is right in the middle, centrally loaded. And if that is the case, you clear it up, you get 48 EI over LQ. Okay? So, a single cantilever beam, it was 3 EI over LQ. Fixed beam, centrally loaded, 192 EI over LQ. And simply supported at two ends, centrally loaded, 48 EI over LQ. So we're going to do a problem here, and this is a beam which is loaded in the middle using some mass. You put a mass there, and basically the mass is as if we have a fancy spring here with that mass in it. So what we want to do is the frequency of oscillation of this structure. This is a single degree of freedom because you have a fancy spring here with the stiffness that we just discussed a minute ago, and you have a mass here which wants to go up and down. We're ignoring the mass of the bar. We are ignoring that. This is made. You have to know what the mass of the mass of this block is. You have to know what the Young's modulus is. Young's modulus of Shear is 30 million psi or 200 GPa. Remember, almost 200 GPa or 30 million psi. We are using the imperial units here. Now, the mass is not 50. This is the weight. Okay, so first thing that you want to do, because there's an I involved, we need to do the cross-sectional moment of inertia. Okay, which is 1 over 12 BHQ. We are told that this is a square cross-section, each side being 2. So Doesn't matter, B is 2, H is 2, so plug it in, you're going to get this number. Now the weight is going to be, the mass is going to be the weight of 50 pounds divided by G in imperial units. Imperial unit, G, if it's feet per second squared, is 32.2. But if it's inch per second squared, since I'm using inches here, look, PSI, inches, then I have to multiply this thing by 2. So 50 divided by 386 is going to give you this weird unit, okay? So plug it in the expression for K, you have E, you're told what it is, you have I, you just calculate it, the length of this thing is the length of it is 6 feet, which is 72 inches, right? 6 feet, from here to here, 6 feet, which is 72 inches, plug it in, and you're going to get the stiffness of this fancy spring. And of course, then you plug it in, K over M, and it's going to be 63.5 hertz, okay? 63.5 hertz. Good. Uh, for a structural component, this is relatively large. In other words, you don't want the frequency of oscillation to be that many hertz on the top of a building. Okay. The last problem that I want to do today is this one, because you see problems of this type very often. You have a bunch of springs and there is a rigid, this is a rigid bar, okay? Rigid bar pivoted there. So obviously if you move this thing down a little bit and let it go, this will go up and down this way, up and down this way, and it oscillates at some frequency. This is a single degree of freedom system because a single variable theta, that angle, this the tells you what the position of the entire system is. Now, I'm going to do this thing two ways. One of them is assuming that what you see there is the equilibrium position. In other words, you look at this beam, it's sitting like that without any oscillation. Just you let the beam go and it looks horizontal and there are springs here. Now, what this tells you is that this beam, this spring is going to have a force in it because because this is not right in the middle. There's going to be a compression here and probably a tension there. So in the horizontal position, there is already a force acting on this bar to keep this thing horizontal. Okay? Now we are not doing any vibration yet. Then you take this and push it down a little bit on the side. If you do it and let it go, then it starts going up and down and up and down. So vibration is going to take place. So I want to find the natural frequency of vibration of what you see there. And I'm going to draw the incomplete free body diagram. The reason I say incomplete free body diagram is because notice that there is a reaction force at O, which I didn't put it here. I didn't put it there. There is think about it as a weight here, right at the center of this bar, tilted bar. There is a weight. I did not put those things there because, first of all, this reaction force is going to go right through O because eventually I'm going to take moment about O. So that reaction force, although I didn't draw it and I don't know what it is, it actually has no moment about there. And the mass, this mass, or the weight that is right at the center, does not have an effect because I'm assuming this is the equilibrium position. I will come back and see what happens if the equilibrium position was not actually horizontal, it was tilted, and then we do the oscillation about that position. We'll do that later, okay? For now, this is the equilibrium position. So we look at oscillation from the equilibrium position. That's why the weight is going to cancel out. You will see that later on. Okay, so these are exactly what I told you just a minute ago. So what we're going to do is sum of all the moments about the point O equal to J about the point O, whatever it is, J about the point O. And let me remind you, J about the centroid. If you look in your strength of material book or deformable bodies book, Ebler's book, you see that J about O is 1 over, I believe, 12 ML ml squared, your ml squared. But if you have it about a different point, you have to use the parallaxis theorem. Okay, so I will leave it to you. We pretend we know J about O. It requires the use of the parallaxis theorem. Okay, yeah. So we come here. Uh, Write all the moments. I've assumed that this is the direction, positive direction of acceleration. All the moments. So this is going to give you a negative moment, and so is this one, negative moment about O, because this is my positive direction. Okay. So J O theta double dot. All the moments about O, these are both causing negative moment, opposing this, and clean it up. You're going to get that expression. Okay. Now, if you look at this, this is the mother of all equations for this problem. If you say, what plays the role of mass? Well, JO plays the role of mass. Okay. What plays the role of K in the formula square root of K over M? It's this whole thing that plays the role of KM, K. Because remember, the mother of all equation was mass times x double dot plus kx. So if it looks like that, whatever is multiplied by double dot is the mass, play the role of that mass, and whatever is multiplied by the thing that does not have derivative plays the role of the stiffness. This is the stiffness, equivalent stiffness of this fancy spring, and this is the equivalent mass of that fancy spring. So you plug it in, K over M. This is K. Remember, I say K is this whole thing. Oops. This whole thing. And divided by M. This is this JO. And there we are. Now, what if actually the equilibrium position was not that horizontal position? In other words, uh, yeah, if I include the weight at the CG, then the situation is like that. There is no oscillation. If there is no oscillation, this is a static problem, okay? And if this is the equilibrium position, then what it means is that there are forces built into the spring, and the when you take the moment of all these things about O, you get zero. So this is the case. Okay. Sum of all the moment about any convenient point. So here I'm assuming that distance from here to here is actually C. This C that you see there, this C is that distance. Okay, that distance from the center of mass to the point O. Okay, now from this position, I will actually tilt it a little bit. I force it down and then let it go. So it starts to oscillate about that equilibrium position, this tilted equilibrium position, oscillate about this. And when you think about it, this is a complete free body diagram because I put the reaction force at the pivot, which is totally unnecessary because this gives you moment zero. And this is the weight which I'm going to take moment about the pivot point. And P1 and P2 were already there. P1 and P2, think about it, were already there. But if you tilt it a little bit more, there is an additional, think about it as additional force, upward force, which is resisting that motion. It's KB theta, and an additional downward force, okay, which is Ka theta. And if you wrote the sum of all these moments about the point O, sum of all these moments about the point O, you're going to get this. Just literally go ahead and multiply it by the moment arm. But what you see here, this expression appears, but this expression is zero because of what we had up there. P1 times B, P2 times B, P1A plus MGC is exactly that. So this actually goes away. This actually goes away because it's zero. Okay? And therefore, the equation of motion is this, the mother of all equation. is right there, and it's the same equation that you got before, and the natural frequency is going to be the same. So this kind of wraps up the lecture, and this is what I did in class. Now, usually when I do these recordings, they're a few minutes shorter than whatever lecture was presented. The reason is that there is some interaction with the student. There's questions and things like that. That's why the lectures, as done in class, they're maybe an hour. Well, it is actually an hour and 20 minutes, but here it's only an hour. Okay. All right, folks. So when we come back on Thursday, we're going to be doing we talk about the energy equation and a whole bunch of problems that we're going to do, and we'll worry about it then. All right. Good luck. See you on Thursday. By the way, I'm planning to post the homework, which is to be discussed today. And the reason being that in the lab, somebody told me that because you have a lecture Thursday morning, followed by a lab at 4 p.m., uh, and some of the homework problems may be related to the material that was discussed on in the morning. Would it be possible to post these things earlier? Well, the thing is that when the lecture and the lab are on the same day, this is inevitable. However, I try to put not too many problems. Like last time, it was only one problem on the homework at 4 p.m., which was actually needed the material from the morning class, one problem. And so I try to minimize the number of problems that actually, requires stuff from the earlier material earlier that morning. That in spite of that, I will post the homework for you today. There's one or two of them that require the things that we do Thursday morning, but there's only one or two of them in that boat. Okay. Good luck. See you on Thursday.